Okay, so today I want to talk about integration on manifolds, and there are a number of things that one needs to keep in mind when one talks about integration on manifold, particularly what is integration on manifold, how to do it. And we're going to build up slowly. So the point here is that I want to expand on the meaning of this expression. So I showed you the last time that all the fundamental theorems of calculus that we're familiar with, fundamental theorem of calculus, one-dimension, Green's theorem, Stokes' theorem, the divergence theorem, Gauss' theorem, they're all one and the same thing. And then one and the same thing is what we call geometry, Stokes' theorem. Generalized Stokes' theorem. And this is the statement that given some n-dimensional manifold, M, n-dimensional manifold, and some P form, some M minus 1 form omega, that the integral of the exterior derivative of this m minus 1 form, the exterior derivative takes m minus 1 form and makes it to an m form, which I integrate over the n-dimensional manifold, is the same as the m minus 1 form integrated over m minus 1 manifold, called the boundary of M. And if you think about the structure of this, it says that the integral of the derivative of something over some region M is that thing evaluated on the boundary of that region. So it has the same structure as all of the fundamental theorems of calculus that you're already familiar with. I've shown you this the last time. Show it to you, but I gave you some hints that it's where it's true, this is why it's true, and that's the structure that we're working on. However, there are many things that should disturb you about this step. One is that I've told you how to integrate over a manifold. So what does this integral sign actually mean? Right? And it's all well and good to say that integral of some form. So what does the integral sign mean? Second thing is, we have spoken about this before, but it's worth revisiting these ideas just to refresh our memories. How do we get the boundary of a manifold? Right. We already encountered this in the last lecture where I said that the fundamental theorem of calculus applies to an integral over the region from A to B. So it's some finite subset of the real line. Right? And if you think about it, a finite subset of the real line is slightly problematic if you think about it as a manifold. Everywhere inside that subset locally looks like the real line. Right? We said that a manifold was something that locally, a d-dimensional manifold was something that locally looked like R to the d. So one-dimensional manifold is something that locally looks like the real line. So every point inside the interval from A to B, okay, that looks like the real line. But what about the endpoints? Right? What's to the left of A? What's to the right of B? So locally, these 2 points don't look like the real line. So how do we think about those in terms of manifolds? Okay. Like I said, we have already covered this earlier when we were talking about the structure of manifolds and stuff. The way we think about it is to broaden our definition of what a manifold is. So it should locally look like R to the D. Actually, it should also locally look like it also could locally look like H to the D, the d-dimensional upper half plane. Okay. The d-dimensional half plane. So I just want to revisit these ideas, put them into context here, but that will tell us what this boundary is. Then we need to express what this integral is. In particular, we need to say, can we do integrals over any manifold? The answer is no, we can't do integrals over any manifold. We can only do integrals over what are called oriented manifolds. Okay, so now I need to tell you what orientation is. And you would suspect orientation has to do with left-handed and right-handed movements, and whether you can uniquely, unambiguously define an orientation on a manifold. If you can unambiguously define an orientation on the manifold, then yes, that is an orientable manifold. So an orientable manifold is one that is equipped with an orientation. I will expand on this now. If you can't unambiguously assign an orientation manifold, that is to say, you can't unambiguously assign some, let's say, right or left-handed coordinate system to the manifold, then the upshot is you aren't able to integrate on that. Okay, so for example, one canonical example of an unorientable manifold is the Mobius strip. Mobius strip is an unorientable manifold. You can't integrate, you can't define integration on a Mobius strip. Similarly, you can't define integration on a Klein model, etc., etc. Okay, so these are interesting concepts, and they're not just academic things that only mathematicians would care about. It turns out that in some contexts of knot theory, where you need to calculate things by integrating over surfaces that the knot traces out, you will run into these kind of non-orientable surfaces. We may or may not come back to how you resolve that later in the course, depending on time. So let me break up these things into their various parts, and we'll take them step by step. And ultimately, I want to be able to give you a well-defined notion of what this equality means. Okay. So let's start off then with the idea of the boundary of the manifold. So an n-dimensional manifold with boundary is a topological space. So n-dimensional manifold with boundary is a topological space. Again, we'll cover this. I'm going to go through the little parts. So, is there anything sound clear? Topological space that they can, that's equipped with some trots. Let's say phi alpha takes u alpha to r Vm, or phi alpha that takes u alpha to h to the n, where h to the n is the set of x1 to xn and r to the n, such that x to the n, sorry, so that xn is greater than or equal to 0. Okay. Again, we've talked about this. This is the half plane in R to the n. Half space now. So this would be half space. So why are we in this? Well, if we allow our chance to map from u alpha to r to the n or u alpha to h to the n, then we allow for the possibility of points like A and B in the real line. So points that are boundaries of n. Just continuing with our definition, we also need that we also need that the transition function phi alpha composed with phi beta inverse on overlap alpha intersection beta smooth is smooth. So I should tell you then technically how to define a smooth function on the boundary. So we will say that a function on h to the m is smooth if it extends to a function on the manifold where I require that h to the m is greater than minus epsilon, some positive number epsilon. Okay. So these are just technicalities that we will need and that we won't really use in practical purpose for practical purpose.
Yeah, sorry, what is phi of b? What is phi of b?
So I have two charts, right? U alpha and U alpha and U beta. This is the transition function that takes you between those charts and the overlap. So if you go back to the picture that we drew, this phi beta takes you from R to the N onto U beta, and then phi alpha takes you to R to the N. Okay. We will say that a function is smooth boundary on h to the n. On h to the n is smooth on settings 1 to xm such that xm is greater than minus epsilon for some epsilon greater than zero. The point here is that this is a manifold by our normal definition. Okay. Given this, we will call the boundary of the manifold M is a set of points of this points P and N such that some chart phi alpha taking U alpha to H and maps the point P in M the point in the set x1 to xn such that xn is equal to 0. This set here is called the boundary set of the manifold. It's the boundary of the manifold after we identify part of the end. Okay. So that takes care of what this object is. Again, Sturzer theorem tells us how to do integrals over the manifold, and related to integral or the boundary of the manifold. And technically speaking, this is how you construct the boundary of the manifold. My next statement is that you can only do integrals forms on oriented manifold, orientable manifold. Let me tell you what an orientable manifold is. In order to understand what an orientable manifold is, we need to understand the idea of orientation. So suppose I have a connected manifold M. Remember, connected means that I'm drawing any two pieces, any 2 points in that manifold with some continuous path. Yes, so this manifold is not broken up into pieces. So let's M be some connected m-dimensional differential manifold. I'm going to pick. So let's pick some point P. And I'll be let's say UI be a chart containing P, some set of local coordinates we call X mu. UI be a chart containing P with local coordinates X mu. Now I'll pick another chart. Let's call it UJ. That also contains P. UJ, another chart. So, final form. First thing I wanted to satisfy is that the overlap between UI and UJ is not empty. Then let's pick local coordinates on UJ. I'm going to call those local coordinates, let's say Y. And finally, I want the point P to be an intersection of UI and UJ. P on the intersection of UI and UJ. So now, given these two charts UI and UJ, see what we can say about them. Well, the first thing to note is that tangent space of the manifold on P can be spanned either by the set d by dx nu, the set of tangent vectors at that point in the x coordinates, or the set of tangent vectors at that point in the y coordinates. Okay. So GP of M is spanned by either E mu. So E mu defined to be mu by dx mu, or let's say E mu tilde will be the set E by E1. Okay, either is fine, depending on the coordinates that you expect. But I also know, because the point P lies in the overlap between Ui and Uj, that these two coordinate systems are related to each other. And so these two bases are related to each other. And they're related as follows: the E mu tilde, or let's say E mu alpha, are dx mu by dy alpha E mu. Now, what does this do orientation? If the Jacobian of that transformation between these two bases for these charts that define these conditions, this manifold, if the Jacobian J is defined as the determinant of this matrix dx mu by dy alpha is positive on the intersection, then the two basis sets, E mu and E mu tilde, are said to define the same orientation. That is to say, if this is a right-handed coordinate system, then this is a right-handed coordinate system. Okay, this map between these two that comes from the transition functions does not if I have a right-handed coordinate system, it doesn't flip it to a left-handed coordinate system. Okay, so if the Jacobian is positive on this intersection, then E mu and E mu tilde define same orientation. On the other hand, if the Jacobian is negative, then they define the opposite orientation. So given this definition, if M is a connected manifold that's covered by some set of charts UI, then M is orientable if for any overlapping charts UI and UJ, I can find coordinates x mu and y alpha such that the Jacobian is positive, right, for any overlap. So for example, the Mobius strip that we identified already as a non-orientable manifold, there's some overlap where I have to take a cylinder, take a rectangle, right, and then I have to twist it and glue it. So that overlap region, in that overlap, this will not be true. Okay? In the gluing overlap. So the manifold M is called orientable if for any overlapping cross Ui, then Uj, we can find coordinates x mu and y mu respectively. Let's say the x I and the x mu and y from j corresponding to the y outputs such that j Jacobian spot. If M is a non-orientable manifold, then J can't be positive on all the charge intersections. Examples here, the Mobius strip. Everybody knows what it looks like. Yes, just so Mobius strip. About that. The Mobius strip is just cylinder with a twist. So you take a rectangle, you twist by 180 degrees, and you do those two edges together, and you'll get this object here. The point here is that I can define some coordinate system, let's say dx, dy, and if I propagate this thing along this curve, then through the twist, it gets flipped. If I start here, I'm getting through, come back, it'll flip. So start with dy dx. Yeah. And then as I come across the flip, as I come across the twist, it flips around. And the point is that this is then being propagated. So I don't have a unique unambiguous definition of my kind of coordinate system here. So that's what happens if you don't have an orientable manifold. Yeah.
Sorry, I was having trouble with the definition of orientable. Is that definition essentially that we can find a collection of open charts UI such that all the Jacobians share on
The overlaps.
yeah, those UI cover
Yes. But I'll always talk about an atlas, which is a collection of such charts. And so when we're talking about the overlaps, we're talking about the overlaps of the atlas. Okay, so this is what happens if you have a non-orientable manifold. And the point here is that on a non-orientable manifold, you cannot do integral calculus. And there's a reason, there's a good reason for this, and let's go back to philosophy of what the integral is relative to what the derivative. I think you do differential calculus on an orientable manifold. The differential calculus involves, as we've seen, comparing nearby points to each other. So nearby points to each other are perfectly well defined, and I can define a derivative on an obvious script, no problem. Integrals, on the other hand, are global links. They involve counting up things that over a distribution of locations on your space. In this case, we'll, where this fit is translationally invariant. So you can always find on the overlap region that you run into this problem of non-positive integral. So where you can't do integration obvious. What can you do if your manifold is orientable? Well, if it's orientable, then we can always find what's called a volume form. So if I have an m-dimensional manifold, this is an m-dimensional, this is an M form that is everywhere non-vanishing on the manifold. So if I have an m-dimensional orientable manifold, I will always be able to, and I'll show you how we can canonically construct one. I can always find some M form, right, that is nowhere vanishing. And to this, I can ascribe the volume of that earth. Roughly speaking, counts the size of it. Okay. So if M is an m-dimensional orientable manifold, we can always find some M form I'm going to call it breaking with tradition vol. This M form will be the volume of the manifold. Like our, for example, comes back omega. I'm going to go with this because it will make it a little bit clear what we're doing when we do integrals. This is called the volume form on M. Oh, volume. Let's say volume element. Which is nowhere vanishing. This volume form law plays the role of the measure in the integral when we do an integral of a function on the manifold. So you write the integral of a function on a manifold, and I said that we integrate M forms on m-dimensional manifold. So if I've got an m-dimensional manifold and I want to integrate a function with the zero form, then I need to supplement this function with the measure of the integral. The measure is played by the role. The role of the measure is played by this guy. The role is played by this guy. Okay. There's some points that are worth noting here. One is that two volume elements are considered equivalent if we can find some strictly positive function such that the one volume element is that strictly positive function times the other volume element. If I can find this, then those two are equivalent. So ball and or prime are considered equivalent if we can find some H in set of functions on manifold that's greater than 0. Strictly greater than 0, otherwise we're doing this condition again. With ball equal to H and ball prime. If the function H is negative definite, then we have an inequivalent orientation. And what this means is that in a manifold that is orientable can be put with either a right-handed or a left-handed orientation. Okay, so that's where this comes from. It comes from the sign of A. So this means that what we chose to call a right-handed orientation here could just as well be defined as a left-handed orientation, and it will be consistently a left-handed orientation on the manifold. And basically, you will also put it back with the interest. So that's point 1. Point 2 is that so I said that there's a canonical volume form to be defined on a manifold. So suppose I have some n-dimensional orientable manifold M, and it has a metric G. Then we can construct this canonical volume form the following way. G. One, cover M with oriented charts. 2 in any chart. We let G mu be G acting on d dx mu d by dx mu. Let's fix the components of the metric and the coordinates x mu in the chart there. And then 3 define the object ball be the M form given by square root of the absolute value of the determinant of the matrix of numbers G mu. What relativists would call G, G, but we're reserving little G for the actual rank 2 tensor. dx1, dx2, 1 derivative dx10. So, as per our definition, so that we were non-vanishing, it's clearly satisfying that property. However, we need to show that it transforms appropriately. To do that, one piece we need to fill in is how this thing transforms. What we know about volume form is that it should remain invariant under change of coordinates. Right? Otherwise, if you make a change of variables and you're trying to do an integral, and the data doesn't change, that doesn't remain invariant, or doesn't count Jacobian appropriately, rather, then you're going to get a different answer for the integral. You don't want to change variables to do. So we know that we have appropriately defined change of variables. I need this volume form to remain invariant under change of coordinates. So let's make a change of coordinates. So if we pick some overlapping chart, to R to the N. In which the metric has components G mu prime. Let's say I pick coordinates from this x mu prime. The metric has components G acting on D by dx prime mu, D dx prime mu, like such. Then the volume form in these new components and these new coordinates is vol prime, and this is square root of mod determinant of G mu prime dx prime 1 mu dx prime m. And the point is, on the overlap, where these two things, where these two charts overlap, vol prime and vol must be the same. Okay. So let's see if that's the case. First point is on the overlap. So on U section U prime, dx prime mu is some t mu dx mu. Where this guy is as usual, dx prime mu by dx mu. And these guys, the dx primes, are related to the dx's. As follows: the dx prime 1 to dx prime m is dx prime 1 by dx1 where to dx prime m dx m dx m. And these coefficients here, counted in the symmetric way, is nothing but the determinant of that matrix T times dx1 dx. In some ways, the definition of the determinant. Or P mu u prime, which remember is just G on the prime mu d prime mu, where d prime is d by x prime, d by dx prime, is just G of d x say alpha dx prime mu d by dx alpha, suppose the alpha dx beta by dx prime mu beta. I can pull these guys out because G just acts on the basic vectors. This is nothing but T inverse, and this is nothing but T inverse as well, if you look at what T is. So this is T inverse, the alpha mu component of that, T inverse, the beta mu component of that, times d alpha beta. And then I can take determinants on both sides, and the determinants factorize. So follow that the square root of the absolute value, in fact, so the determinant of G mu prime is the determinant of T minus 2, because the determinant of the inverse is 1 over the determinant, and the determinant of mu. So this is an oriental manifold, then this is a positive number, and I can take the square roots, and it follows then that I get one factor of the determinant of T from here, and I get one factor of the determinant of T, 1 over one factor of the determinant from here, which means that all prime, same as, and indeed, volume element is invariant. Okay. So I want to stop here. I was going to go straight on to defining integrating, but halfway through the book, I realized that we have all of the tools that we need to make something that said already a little bit more precise. And that was a statement that as vector spaces, the set of P forms on an n-dimensional manifold dual to the set of m minus P forms on that n-dimensional manifold. Remember I said we had these two vector spaces and we were just counting basis elements, and we found that the basis element of the set of P forms with the basis element of the set of m minus P forms with the same number of basis elements. So they were the same dimension as I go up in P and then down in and then down in minus P. Well, now we have to ask the question. Well, okay, we're always going to get this one, but we're going to ask the question: how do we actually realize this duality between P forms and M minus P forms? Okay, and we realize the duality, well, like any duality in quantum vector spaces, you realize the duality through some inner product, and in this case, it's the inner product of P forms. Now we are able to define because you need something called a Hodge star operator, right? And what we needed to Hodge star operator is this idea of modular. Now we have this. So next time I'm going to make a small digression from the story we're trying to build here, and I'm going to tell you how to define a Hodge star operator. Once we have the Hodge star operator, we'll put on that, which we'll come back to when we talk about the round cohomology, and then we'll return to the integral sign, finish defining everything out there. There's not too much to do there because we've done all these integrals since first year already, and I'm not telling you anything new. I'm just showing you how to get pretty full. Then we'll have finished defining integrals. What we really want to matrix this course is the idea of the round cohomology. That's where we're going to get to our points. Okay, we're putting together all these puzzle pieces, and they will come together in the idea of the round cohomology. All right, thanks.